Hello, good afternoon. We are here today for one more power and energy webinar. I have a little presentation to introduce my guests. I will share my screen just a second. Okay, guests, please let me know if you can see my screen. Can you?
Yep, all good.
Okay. So today's webinar is called From Simulation to AI, Tackling Fault Detection and Classification in PV Systems. We'll have Celestino Silva and Olga Tiagina with us, and I, Bernardo Silva, will be the moderator. So, Celestino Silva will be the first speaking. He's researcher in SPAES, Center for Power and Energy Systems at INESC TEC. His expertise is in machine learning and data analysis for the challenges in the power systems. He has a master degree in PhilP from 2024, and he has been focused his research in generating data sets using MATLAB Simulink environment and on machine learning strategies to identify patterns in data from photovoltaic plants. We then will have Olga Tegina. She's also a researcher in INESC TEC, the Center for Power and Energy Systems. She has been working on machine learning techniques to real-world challenges. She has a master degree in information systems and technologies from 2022. And her research focus is in time series data, including as forecasting, data augmentation, and utilizing graph neural networks to capture complex relationships in energy networks. Well, for today's session, Celestine will be the first with a presentation called Fault Detection and Classification in Photovoltaic Power Plants. And then we will have Olga with the theme Exploring Graph Neural Networks, Fault Location in Photovoltaic System. So, our goal in this webinar is to present and discuss ideas, expected outcomes, or results regarding the energy systems of the future. How we do it, these will be two presentations, 20 minutes each, and then at the end we will have 10 minutes questions and answers that you can make through the dedicated area in Zoom, and I will assess your questions and put to the presenters. If you want to present, please send us an email to energywebinars@inesctech.pt. And do you want to attend? This is strange to have it here because if you are here, you are already attending, but follow our link on energywebinars.inesctech.pt. Thank you very much. I will now pass the word to Celestino. Celestino, please, 20 minutes. The floor is yours.
Let me just share the screen. Can you see the screen?
Yes.
Okay. So, good afternoon, everybody, or good morning, depending on where you're watching us. Thank you very much, Bernard, for your introduction, and thank you all for attending this webinar. First and foremost, I'd like to express my gratitude for the opportunity to take part in this session as a speaker. As previously stated, and I'll repeat again, I'm Celestino Silva, and I'm a researcher at INESC TEC since 2024, this year. The subject I'll be discussing today is with the focus of my master's thesis, which I also completed this year. It was supervised by Professor Rui Esteves Araújo, whom I'd like to sincerely thank for his exceptional support and guidance throughout this research. So, the topic I'll be addressing today, as you can see here, is fault detection and classification in photovoltaic power plants. So, in this presentation, the context and motivation of this work will be discussed, alongside with the objectives, the considered case study, the results obtained, and the conclusions and future work. So today we live in an area where the need for finding sustainable energy solutions has never been more urgent. As we face the growing consequences of the fossil fuel consumption, renewable energy sources are emerging not just as alternatives, but as essential components in mitigating climate change. Among these sources, photovoltaic systems stand out for harnessing the most abundant resource available to us, the solar energy. PV systems are primarily known for their reduced environmental impact. However, they are not free of challenges. As they are installed outdoors, they are subjected to various adverse conditions that can reduce their performance. This is why continuous monitoring and maintenance are crucial to ensure optimal performance and longevity of the PV systems. This is where Industry 4.0 advancements come in, revolutionizing our ability to collect and analyze large amounts of data from the PV systems. By using this data effectively, we can predict and prevent potential issues before they become major problems, offering the potential to improve fault detection and classification and optimize PV system operations. As most of you may be aware of, a fault is defined by any factor that reduces the output power, thus affecting the efficiency of energy production. In PV systems, faults can arise from electrical malfunctions, environmental factors, for example, dirt or shading, wiring issues, for instance, aging or degradation of components, or improper installation, all of which can compromise system performance, efficiency, and reliability, if not identified and addressed in a timely manner. The consequences of these faults can lead to reduced energy output, increased operational costs, and potentially safety hazards. To overcome this, fault detection and classification are essential. Fault detection aims to identify whether a fault exists in the system or in the component by uncovering anomalies or deviations from normal operation. Fault classification, on the other hand, involves determining the type of or the nature of a certain fault. Effective fault detection and classification help with reducing system downtime, improving maintenance strategies, and ensuring operational safety. Generally, in these cases, there's a lack of available faulty data or even any type of data. To address this matter, I found this image that describes the solution of using a digital twin that was extracted from this paper. So the digital twin concept for PV systems involves creating a detailed and dynamic model that mimics the behavior and the performance of the real infrastructure that allows for the simulations of various scenarios. This image illustrates a machine learning prediction model built using historical generation data. The training process involves using historical data to train the model, which can forecast future performance and identify potential faults. These results from the machine learning model can be compared to the data from the real PV plant to determine if there's any deviation and alert the O&M teams. Both in this paper and in our case study, the machine learning models are not connected to a real PV plant. The model is built using only historical PV generation data. Therefore, the focus is only on predicting future performance based on past data without any interaction with the real PV system. So, the main objectives of this study is to explore methods to recognize patterns in PV plant data, aiming to effectively identify and classify faults in the system. The goal is to enhance fault detection and classification for better maintenance strategies and optimize system performance. This project also aims to evaluate the performance of the model used. This involves assessing key performance metrics to ensure that the models are both effective and reliable in identifying and classifying faults. So in this case study, the bit configuration is constituted by a transformer, 2 inverters, 8 junction boxes per inverter, and strings. Each junction box has 13 to 16 strings connected in parallel, and each string has 20 modules in series. As previously stated, due to the lack of available data, it became necessary to generate a synthetic dataset with the use of a digital twin. The level of detail in a digital twin depends on the available information about the physical system and it's important to assess the appropriate level of detail for each specific case. Besides the technical specifications, the time resolution, or the granularity, is a critical factor. In this case study, data from PV strings, junction box, and inverters were used with a granularity of 15 minutes. So in our dataset, there are two types of data, the SCADA and the weather. Weather data provides information regarding irradiance and temperature, while SCADA data provides information on electrical measurements, for example, powers, currents, voltages. The idea behind acquiring this data was to first gather the weather data and then use them as input for an electrical model to generate the desired SCADA data. The weather data was extracted from the Sentinel database. This database allows the selection of latitude, longitude, start and end periods, and variables for a specific location. The collected data spans from January 2019 to June 2023, covering a period of approximately 4.5 years for the location of Évora in Portugal. In this work, we focus on faults like DC cable degradation, partial shading, DC cable open circuit, and DC cable short circuit. These faults were selected for being common and because they have a significant impact on the performance of the PV system. These faults are located on the strings connected to the H junction boxes of the first inverter. So degradation refers to a gradual increase in the series resistance in the cable of a string over time. Partial shading results in a reduction of irradiance affecting a string. Open circuit occurs when there's an open circuit in the string cable. And the short circuit refers to a small resistance path between the positive and negative terminals of a string. So, first, different types of days were analyzed, such as clear and cloudy skies in the winter and the summer, and irradiances were extracted to observe the differences between each type, as we can see in this image. Through the digital twin, it is possible to simulate the grid's behavior, allowing for simulations with and without faults to generate the desired SCADA measurements. Fault scenarios were created randomly, namely the fault type, the location, and the start time. To observe the differences between each fault type, a clear sky summer day was chosen to make these differences more noticeable. Additionally, the same fault start time and location were selected for a better visualization of the graphics. These rules can be observed in this image that represents the string currents for each fault type. As we can see, until the fault happens, all of fault types present the same behavior, and after a fault happens, the string currents have different behaviors according to each fault type. So, the dataset randomly generated is unbalanced, as there are a significant disproportion between the different classes. This figure shows that most of the data points belongs to the no-fault class, and short circuit and shadowing are much fewer. Strategies to address this issue of unbalanced dataset include applying our algorithms suitable for handling imbalanced datasets and using robust evaluation metrics. One of them is F1 score that will be later explained. So the concept of feature creation was used, which involves creating new features that hold relevant information. Therefore, time-related and weather features were added. It was also applied the feature selection process to select only relevant columns, removing the features that didn't have meaningful information. Regarding the train test split, for a better understanding of this process, this table shows the total number of days for each data type present in the dataset. The division of data into train and test sets involves selecting the days to ensure that the model is trained across various conditions and can evaluate new scenarios accurately. It is important to note that the test days were selected through a uniform distribution. This process ensures that the test dataset is representative of the whole period covered, avoiding any bias that might arise from selecting dates that were too close for each other. Additionally, the split was done to ensure the same proportion of data types as in the full dataset, ensuring that the model is exposed to a diverse range of conditions during both training and testing phases. So this slide shows the percentage of each class in the training and in the testing dataset. As we can see, the class distribution is consistent across the entire dataset and in both train and test. This means that the data split is well balanced regarding the fault classes, which allows the model to train well and generalize effectively, illustrating the real behavior of the overall dataset. As for fault detection and classification techniques, several methodologies can be found in the literature. The chosen technique to address this challenge was machine learning, due to its ability to learn patterns and relationships from large amounts of data, making it highly effective in identifying and classifying faults in complex systems, for example, the PV plants. Machine learning models can improve over time for continuous monitoring and accurate fault detection and classification. So, numerous algorithms were considered and analyzed, but the one that stood out was LightGBM. It involves training a sequence of decision trees, each aiming to correct the errors of its predecessor. LightGBM uses a leaf-wise tree growth method that expands trees by selecting the leaf with the largest loss reduction split, making it more efficient. This algorithm is also especially useful in context of complex and high-dimensional data, such as fault detection and classification in PV systems. This algorithm was chosen after a series of experiments competing with other models and showed the best performances. So, regarding the choice of the chosen metric, FIUN score was used, as I previously said, as it computes the harmonic mean between two others, precision and recall, that analyzes the impact of false positives and false negatives, respectively. Given the imbalanced nature of our dataset, the macro FIUN score was used, as it treats all classes the same way, regardless of their size, unlikely the weighted FIUN score. This ensures good performance across all classes. LightGBM is also robust to imbalanced datasets, where parameter tuning can be performed to find the best combination of parameters that optimize the model. For the pipeline selection, two types of simulations were performed. The first aims to analyze the impact of different feature groups on the performance metrics, while the second one chooses the best combination and performs hyperparameter tuning. So, regarding the first simulation, the feature selection, both weather and JB feature groups are highly important, with JB emerging as the most critical one. This group is crucial for the model's good performance because the main differences in the SCADA data are precisely in this group. It's also important to highlight that these results are ordered by this metric, the macro FIUN score. Then, the best combination, the first one, suffered hyperparameter tuning, which led to the following results. So, the model achieved nearly identical macro FIUN score and accuracy values for both training and testing datasets, with both metrics averaging around 80%, demonstrating that the model's consistent performance across both training and testing. The macro FIUN score is particularly notable as it was the most relevant metric and it was significantly improved by the model, highlighting its overall effectiveness in handling all classes uniformly. It is also observed there's a confusion between no-fault and string cable degradation. This confusion can be explained because these two classes have similar conditions, so this leads to a very confusion between these two classes. So this analysis highlights the importance of evaluating different feature groups combinations to optimize model performance and generalization in both training and test datasets. As previously said, the JB group of features is critical for better model performance, and therefore this model proved to be suitable for fault detection and classification. Future work will focus on improving model performance by balancing the dataset through the collection of more fault data from minority classes and analyzing different weather conditions in the dataset. Other improvements include trying more precise feature selection process by testing with different feature groups, as well as the generation of new features. One more point to be analyzed is to use more complex models, for example, neural networks, for the classification task, and possibly merging with fault location task. So thank you all for attending my presentation, and for my side, that's all.
Thank you very much, Justina. Sorry, it was jammed a little bit here. I was trying to unmute and to connect the video, it was jammed. Thank you for the presentation, Olga. I believe that now we would pass to you, 20 minutes. We will make the questions at the end.
Okay.
Okay?
Of course.
For the audience, if you have questions, please put in the Q&A.
But so far, there is quite a short one. A short question.
But let's make it in the end, okay?
Okay.
So please, the floor is yours, Olga.
Okay. I hope that you will see my screen in a second.
Yet.
Entire screen. Okay. And PowerPoint. It should be all done.
Yeah.
Okay, so as it was already mentioned, my name is Olga. I'm working in SPESH in Center for Power and Energy Systems for the last almost 3 years, under the supervision of Dr. Ricardo Bessa. And today's topic is exploring graph neural networks for a task of fault location in a photovoltaic system. I will give you a brief introduction to what is graph neural network in general, where can they be applied. Celestina already gave you some introduction to our data set, and I will explain it a little bit in a different way. There are also some results on our application of graph neural network to different topologies, and then conclusion, and I will try to answer the question, when do you actually need a graph neural network, or where you can use some other methods. So introduction, a very brief one. Again, I just put a picture of a very big solar farm somewhere in USA to show you the scale of how problematic this system can be, because imagine how many panels are introduced in the system, how many wires, how many junction boxes, switches, and any part of that can break at some point. So in order for this system to work efficiently and to produce the maximum possible power, we need to locate, classify all faults on time, and tell to the operator to fix everything as soon as possible. So for that task, now it's emerging task to implement some machine learning and neural network techniques for that, to help the operators to locate the faults. And in this presentation, we had to answer two questions. Well, first of all, is it possible in general to locate a fault in a PV installation with machine learning models? And if there are any advantages of using graph neural networks over traditional machine learning models. So what is a graph and what is a graph neural network? A graph is basically a structure, a mathematical structure consisting of nodes and consisting of edges that connect these nodes, like picture is here. Any node can be some kind of participant in a system. For example, it is widely used in social networks where your friends are nodes. And when, for example, Instagram proposes you a new friend, very likely it uses graphs to predict a new edge propose your friend. It also can be used for molecule classification, to create new pharmacy medication, and in many other applications in the world. So graph neural networks can produce several outputs. For example, it can classify graph in general as a whole. For example, the simple example is to tell if it's an organic or non-organic molecule, for example. On the edge level, I already made an example of proposing you a new friend. And it could be a node level classification, which is our case, when it will tell if, for example, in a distribution system, power distribution system, or in a PV solar farm, if a node can be problematic or not. So a graph can be described as a set of several matrices. So it's suitable for a neural network to take this input, process, and give you an output. So as a base for our work, we use this paper that is listed here on the title, for localization for power distribution systems. As you know, the power distribution systems can be spread over several kilometers, maybe tens of kilometers. So the authors propose here to use graph neural network to locate some region where it is most likely to have a fault. And the big advantage of this method in this application is that it is topology invariant. So unlike other machine learning models, it is theoretically possible to train a graph neural network on one topology, and then introduce it to different topologies that it never saw before, that can be in different location, that can be with a different amount of equipment connected. And still the model should be able to produce a reliable and accurate output. And they prove in their paper that for their case, it worked. So the model performed pretty well on the topologies, on distribution systems that it didn't see during the training process. So what we have further is the dataset. And as Celestine already introduced to some parts of that, is we have the same system with the transformer, two inverters, 8 junction boxes, and several strings connected to every junction box. We collect the same measurements here. The only difference between this system and the one that Celestina had is, first of all, we don't only consider strings, we also considered inverters and junction boxes. So in this case, we have more types of faults and a bigger system in general. So how to convert our real PV power plant to a graph, which is some abstract thing. So it's very simple. So we assume that every equipment can be represented as a node, and the wires that connect equipment on land are basically edges in a graph. So as simple as that. This is a simplified example without strings. So when we add strings, of course, the system gets a bit more complex. So in this system, we have 254 nodes, and we also had to add a no-fault node because in the original article, they only consider faulty scenarios, but we also need to check if everything is fine with the system. The model should also indicate that, and it will indicate that this fault is a fault location in this case. So, as I said, we have more fault types now. There are 11, and here is the distribution of them in the dataset. Everything else is the same, so big system and the same digital twin limitations that we had before. One of them is that we don't have faulty scenarios in the real dataset, so we had to simulate them in Simulink, as well as the no-fault scenarios. So we had 5 years of data, and we can see that the distribution of faults is more or less the same over all these 5 years. So we just pick 1 year and split it half-half to have the reserve for validation and test splits. We also considered the fault types to be distributed evenly on the train validation and test sets. So the results, I will first go without topology change. So we don't check how the model reacts to change of topology yet. We just compare it with other machine learning models. And again, I will start with a simpler topology. So we get step by step. This was our first step on this way. We had a smaller system with no strings considered, with less faults also, no strings, meaning no faults on these strings. And in this case, with 19 nodes, we had pretty similar results for LightGBM, for example, for tree-based models and graph neural networks. So in this case, it may be even an overkill to use a graph neural network because you need several days to tune it, to test it. You need GPU, so it also gets a bit faster. So if you have a small system, maybe you really don't need to consider a graph neural network because it will perform better than LightGBM, for example, for only like 5%. However, when we switch to a bigger system, the picture changes a lot. So in this case, when we used already a full system of 200, almost 60 nodes, we can see that graph neural network performs twice better than traditional baseline models. So on complex systems, it may have a lot of sense to consider graph neural networks to use. Even though it takes a long time to calculate, the advantage of them is pretty big compared to traditional machine learning models. And just for you to understand how the output looks like, so it doesn't tell you the exact location, the graph neural network assigns probabilities to each node. So each node is assigned with some number between 0 and 1. To compare it with machine learning models, we took the maximal probability and said that it predicted this class. However, it can also indicate the whole area of nodes, and it can be assigned to check exactly this area, because sometimes, especially with strings, the model misclassified the exact location. But for example, here, it predicted a branch correctly. So it got a hint that probably you have to look here, but it it wasn't sure, as you can see. However, on this example, it was 100% sure, and it was correct that we need to look on this junction box for the fault. And now we also checked the topology invariance change. How did we check it? We simulated more systems. So I just put some systems that we had. We could remove completely one inverter. We could remove several junction boxes together with attached strings. And we tried to see if how the model will react to changes like this. So it's all the same 5 years with the same types of fault. It's just the difference in topology itself. And what we can see here, this is the full topologies that we trained on, as you saw before. On the same topology, it performs, as you saw before, like on the level of 75% of accuracy, more or less. However, when you introduce new unseen topology, the performance will drop a little bit. It is expected, but we are looking for the ways to somehow shorten this drop. But still, it has some ability to locate the faults with some certainty of over 60%, even on the systems that it never seen before. And one of the ways to make it perform a little bit better is to train it not on one topology, but on several topologies. For example, here I picked randomly 2 topologies with 2 inverters and with 1 inverter. And with the red circle, we can see their performance on the same topology. And in this case, overall performance on the model on unseen topologies was a bit better. So it makes sense if you will use it to generate more topologies to be prepared for any change in the field. So I would say the conclusions are here. Both graph neural network and machine learning models have ability to locate faults. However, on more complex systems, it makes sense to give your preference to graph neural network, because even though it takes time to train, still the accuracy is considerably better when you have a lot of classes. However, we have bottlenecks. As we said before, the simulations are not perfect. We didn't yet have a chance to test it on the real scenario, but who knows? Hopefully we will. Yeah, so I hope it was useful for you. Thank you very much for your attention. And if you have any questions, if you need some more introduction, I can give you. Thank you very much.
Thank you, Olga. Thank you very much for your presentation.
Thank you.
Nice drawings looking like in flowers that you have there.
It is aesthetically pleasing to work with it. So
yes, but very interesting work indeed that both of you have presented. So let's check if we have questions. We have one for Celestino, which is, what is GB group of features? Celestino.
Thank you very much for your question. So, as I said, in the dataset, we have several measurements, for example, currents, voltages, the powers. So, what I did basically was I created this JB group that basically has all these measurements from the inverters and the strings. So, when I was trying to make the combinations of these different groups, this group shows that it was really relevant. And why? Because since I'm including measurements of strings and inverters, and since the faults are present in the strings, it's normal that this is a critical group, because basically the differences of having a fault or not having a fault, these differences in currents or voltages will be in this group, and that's why it's a significant group for the performance of the models.
Okay. Then we have an anonymous attendee saying congrats to you two. So proud of you two. Okay, it was not a question, but congrats for you.
Thank you anyway. We don't know who is that, but thank you.
Thank you.
Now we have another question from Kamaru Nisa. My question is related to dataset. Is dataset is labeled, or you label dataset? So is it labeled already, or you labeled it?
It is labeled. It is labeled during the generation. So during the simulation, they know which fault is happening and where. So when you train a model, yes, you need the labeled dataset. So we had actually 2 columns in our data frame. One is where the fault is, and second one is what the fault is, what is its type. So it helped us later to analyze where can be some problems and tune the model better and maybe introduce some new features.
Okay. So from the audience, please, if you have questions, put it there. I have one to Olga first. Olga, if you have a problem, let's suppose in a PV inverter, and you have to be out of service for some days, do your methodology adapt to the new topology that is in place?
Yeah, that is, I think, exactly the use case that can be in a real scenario. So you can not only use this method on a different topology. But if you close something for maintenance, it's not necessary to retune everything and introduce and to deploy a new model. The one that you have on your server should be able to work with that already. But however, as we saw in our results so far, it is not, there is still a drop in the performance on the topology like that. So if we disconnect some part of the system, we should expect that it will not locate the fault as well as it did before on a system that it was trained on. However, yes, it does locate most of the faults.
Okay, thank you, Olga. And Celestino, I have a question for you. In your presentation, you talked about cable faults. Can you elaborate a little bit what could be a cable fault?
Yeah, for example, the faults that I consider was in strings. For example, we have a DC cable open circuit. What is this? Basically, it's an open circuit in the cable that connects a string to a junction box. And we can also have, for example, a short circuit, and this short circuit is in the terminals of between the positive and the negative terminals of a string. We can also have the degradation, that is resistance between the string and the junction box. And we can also have a shadowing, and shadowing basically is a reduction of the irradiance that feeds the string. Those
Okay,
were the results that I consider.
that's raise another question for me, which is when you have a fault, what is the time frame that you are considering for the acquiring the data?
Yeah, the time frame is 15 minutes. So when I generate in Simulink the models, I generate each 15 minutes. So basically we can have for a whole day measurements between 15 and 15 minutes. Like I previously said, that was this granularity or this interval was the one that we choose, so that we think it will be a very good representation of the PV power plant.
Because with this time granularity, which is quite big, fault will happen, will cleared, short circuit will happen, will be cleared, or the cable will burn itself or something. And it will be difficult for you to understand what was the problem, if it is
Yes.
the PV, if it's the cable, if it's the connection.
Yeah, for example, in our generating system, once a fault happens, it will last until the end of the day. So basically, when a fault happens, it will remain until the whole day. So the model can have, like we can say, time to try to see if it gets the right fault.
Okay. Very good. We have another question from the audience with most figure. Kaiman, as Olga told, GNN does better in more complex topology than light GBN. Is this only for location or for classification too?
Yeah, thank you for the question. So far, we didn't implement it for fault classification task, but my expected result here, it's not certain, but it is expected that probably since we only have 11 faults, 11 classes basically, I think it will be more or less on the same level of prediction. So maybe graph neural network be a little bit better, but it will be probably on the same level. One of the reasons why graph neural network performs so well for location is because basically you have to classify 260 classes. So in this case, machine learning methods need much more information to be trained on. So.
Okay. Now we have another question from Mr. Anonymous Attendee. He's asking a lot today. Can you describe the way weather data correlates to your predictions? I don't know for who this
I think it's
question.
So basically, yeah, I have a column that was weather data. For example, in this feature group, you have a lot of measurements and why they are important. For example, if we consider a scenario in summer, the measurements, for example, currents and voltages, will be quite different if it was in winter, because the irradiation is way different. So, for instance, in winter, the model could not be so good to distinguish between those measurements, and that's why it's important to have these weather columns, so that we can tell the model, for example, this is the summer or this is winter, and there are other other columns, and it will have an impact on the prediction of the faults.
Okay. Thank you. Hope this answers the question. I do not have more questions from my side. Q&A. Please, attendees, if you want to put any question to Olga or Celestino, please do so.
I can just
have some minutes.
extend
please.
a little bit an answer, just a little bit. Yeah, we face that during the cloudy days, the performance drops a little bit. So during the cloudy days, it is a bit harder for both models to classify and locate faults. And same during the sunrise and sunset. So apparently, there needed these times have to be explained to the model better. So when it's like darkish, shadow-ish, it needs to be some new features and new explanations should be introduced.
Yeah. They don't know, they don't have any way to know what is happening and why the power is being reduced or increased so fast. Okay, so please, questions. If you have any question, please do so. We still have, I would say, some more minutes.
Yeah, okay, so there are 2 more questions as I see.
There are? Okay,
they
sorry.
are. I'm not
Okay.
sure.
Okay.
Yeah,
Sorry, I didn't went down. Now I do. So how many features are in the data set and how many you chosen? And by which technique? I believe how many features are in the data set?
I think I can answer here for both because the dataset was more or less the same. As Celestino explained in his presentation, he chose groups of features, and in our dataset, it was, I think, more than 500. More than 500, 600 more or less features. It's a lot because you have measurements per inverter, per junction box, per string. So it's a huge amount of features. So the reason, so we reduced them by grouping. We didn't pick all of them to reduce the dataset. And in my case, with graph neural network, I used everything because it was the most straightforward way. I didn't make the feature selection for the graph neural network.
Okay. We have another question. Is your model available somewhere in the internet for more studies?
Mine, no. But the paper that I cited, they have a GitHub, yes, and it's there.
Celestino?
Mine neither. We don't have access to the data set. Is not available in internet, but as I mentioned, there's a paper that also explains the concept of digital twin, and it's a good paper for reading.
In which technique you used for the features selection?
So for feature selection, for example, there are some techniques. For example, we can use trying to see the mean and the standard deviation for the measurements. For example, if we uncover that the mean and the standard deviation of a certain column is way reduced, it means that probably it's not that significant to have, so it's a good column to be dropped, for example.
We have an attendee here with the hands raised. Sorry. Let me give him the word. Victor Tibalongo, can you write your question, please, in the Q&A? Thank you. We have another question here related. Is the data set available? Well, both of you have answered these questions. It's not available, but you mentioned 2 papers. Do you think it's possible to you to put those papers in the Q&A so people could have access to their references?
Yeah, I will search for it.
Okay. Okay, another question. Is there any specific technique to introduce time series to GNN? If yes, can you say the technique you have used?
Excuse me, 1 second. Can you repeat the question, please?
Okay, you are
Yeah.
you are.
I was looking for a paper,
Yeah,
so
yeah. So have a look. Take your time.
I put the it's a direct message. Why it's a direct message? Host and panelists. Okay, this is a paper for GNN.
Okay. Thank you. Well, the question is there any specific technique to introduce time series to GNN? If yes, can you say the technique you have used?
So far, we selected just samples, so it was not continuous time. So it was just a time sample, and we considered them not like a time series, but like disconnected samples. So unfortunately, at this point, we didn't explore that. I'm pretty sure that at least it is possible to add, for example, lag features. For example, at the moment, we only use the current moment, but for some faults, it may be useful to track what was 1 hour before or 15 minutes before. But it would make the data set twice bigger, and it was very big already. So we didn't go there yet. We started with simple things.
Thank you. And right now we don't have any more questions. We still have some minutes. So if there is any more question, please do so now. Let's wait some seconds. If not, I believe we could close that gentleman, Victor. I don't know if he's still alive with the. I see. Victor. He was with his hand raised. I don't know if it was a mistake or not. Victor, if you want, please put your questions in Q&A. Some more seconds. Okay, there is no more questions. So I would finish this session. But before, I would like to thank very much Celestine and Olga for presenting their very good work. Congratulations and good luck for the future, because there's a big road ahead of you, both of you, and you are brilliant researchers that will go through this road. So thank you very much.
Thank you very much, Ronald.
Thank you.
You're welcome.
And
Thank you for all
the
attendees.
participants.
Yeah. Thanks very much. And let's see you again in another Power and Energy webinar. Thank you for attending. See you next time. Bye-bye.